Welcome to my Introduction to Networking course, also known as ITN. This is the version 7 material preparing learners for the Cisco CCNA 200-301. Cisco curriculum, everything is owned and copyrighted by them. Moving on is our data encapsulation. So when we're looking at the OSI model or the TCP/IP model, as data flows through the layers, as they move from layer 6, 7, 6, 5, 4, 3, 2, 1, as they go down, they actually encapsulate into the lower layers. So part of this is we have to talk about why encapsulation is so important. One of the big parts there is segmentation. Taking a chunk of data and making it smaller so that we can ensure efficiency of our delivery. If data is so large, it may be hard to send. So if we break it up into smaller chunks, it will increase the speed and it may lead to increased efficiency. Within our segmentation, we need to number them. That's called sequencing. Basically is we number each segment so that when the receiver gets them, they can put them back. The sequencing number actually helps put them back in order. This is one slide that you definitely want to know out of this lecture. Here is what we would call the data groups as they flow down. The data groups are also sometimes called a protocol data unit, a PDU. So, layer 1, 2, 3, 4, 5, 6, and 7. Data is layers 7, 6, and 5 of the OSI. Segment is layer 4, packets are layer 3, frames are layer 2, bits are layer 1. We need to be able to reference the OSI model against these PDUs. As we're talking a layer 3 data group, it's going to be a packet. If we're talking layer 2 data group, we need to know that it's a frame. So we need to understand this structure. Data encapsulation, literally we take data and we engulf it in a segment. The segment is engulfed in a packet. The packet is engulfed by a frame, and then the frame is put into bits. Here you'll see that here's the data. The data is put into a segment by adding a transport header. The transport header and data is put into a packet by adding the network header. And then the network header, transport, and data is put into a frame by a frame header, and it ends with the frame trailer. That is what it means by encapsulation. Here's a different view. This is an envelope. The data gets put into the TCP envelope. The TCP envelope gets put into the IP envelope. The IP envelope gets put into the Ethernet envelope. And so these are each large envelopes that are placed in one another. Then, as we send data to our receiver, they would de-encapsulate it. Basically, they do the reverse. They will get the bits, they'll make the bits into a frame, they'll remove the frame header to expose the packet, they'll look at the packet detail, they'll take off the packet header, they'll have a segment. From the segment, they'll pull that off, and they will put in data. And the data stream is what application will be using. Moving on is our data access. Basically, our addressing for our data access, both the data link and the network layers use addressing to deliver data. The network layer, source and destination, is responsible for delivering logical addressing known as IPs. The data link layer, source and destination, are physical addresses, and they're used for communication on the same network. Physical, we're looking at timing and synchronization. data link is source and destination physical address. At the network layer, we're looking at source and destination logical addressing. At the transport layer, we're looking at what ports we're using. And all of the upper layers, 5, 6, and 7, that's all about encoding data. Our layer 3 logical address, source and destination, are going to be IP addresses. These addresses may be on the same link, or they could be an external address. There are two major types, IPv4 or IPv6. The nice thing is, as we send data to the internet, it's going to be as IPv4 data packets. When we look at a IPv4 address, we have two sections. We have the part that's attached to the network, and we have parts that attach to the host. Basically, with this, we are looking at the host portions being all of the computer addresses on our LAN. So we could say that PC1, that maybe the first three groups of numbers are part of the network portion, and only the fourth one is part of the host. Basically, that means the network portion would not change, only the host portion would change. Don't fret, we actually have a lesson talking about the network portion versus the host portion coming up. Devices on the same network would use our physical addresses, our MAC addresses. So here we have an example of PC1 and FTP server. You'll notice that the network numbers are the same, and only the host bits are different. These are on the same network. So we rely on our data link address, our physical address, to do our local communication. So let's kind of look at the larger role here. So when a device on the same Ethernet network, the data link frame will use the actual MAC address of the destination NIC because it's all local. And that means the source address of the originating link will use its local address. When we're sending to the destination, it will use the destination. So it's important because when we start talking about what happens when we need to leave the network, then our frame, our physical address, will actually use the destination MAC address of our router. From our router, it will actually then use the next hop MAC address. So here we have a frame. The frame is sent to the router. The router will remove the frame and then add its own frame with the next hop with this address. This router will receive the frame, then it will remove the frame. It will then replace it with the next hop's MAC address. While the IP addresses stay the same, the MAC addresses change. So the role of the network layer address is about being able to stay active as it flows through the network. Because each time the router receives the frame, the router will actually look at the layer 3 address, the IP address. And when it knows, oh, I need to send this IP address to that router, it will use its layer 2 information. So the default gateway is basically an exit point. We're going to run through this. So PC1 wants to send data over to this web server. The PC will send it to this IP address. This is the destination. This is the source. This is the source MAC address. The destination MAC address will be the default gateway, will be the router. it'll be this one. R1 will get it. So here, destination 101, because it's the default gateway. Apparently we're not going to go all the way through. So what ended up happening is R1 should take it as it's the default gateway, and then it will replace it each time with the physical address of the next hop, the next device. The IP addresses will always remain the same, only the MAC addresses will change each time we go through a layer 3 boundary. So the data link address, here, we will use the layer 2 address of the router. The router will then strip it out, look at the layer 3 address, and then forward it accordingly. Going back to layer 2, it will use the layer 2 address, this guy. So the second router will pull it up, it will strip away the frame, it will look at the IP address, and then it will use the next hop, layer 2 address, to send it down the line. All the way through. So we will have a lab for installing Wireshark. We will have a lab going through analyzing local and remote ICMP data traffic using Wireshark. And that is it for this lesson. We learned about the rules, the protocols, the suites, basic standard organizations, the reference models, data encapsulation, data access. The big two to take away from this is the reference model and the PDUs. Those are two things we need to understand. And that is this chapter in a nutshell. If you have any questions or concerns, please reach out.